Ready, howdy everyone. We'll get started. Welcome to another review session. In terms of announcements, the test grades for Dr. Bengali's class, I think have been released or they're being released soon. And then Dr. Altimos should have her grades out by Friday. So be on the lookout for those. If you have any questions from either class, about your test grade or want to go over anything, just come ask me, come ask your respective professor. Either one of us would be happy to go over that with you. And just know you have, I think, 2 more quizzes and then a final. And then that should be the rest of your exam grades for the semester. Your final counts for 25% of your grade, I believe. 20 and 25, either one. But that is a good percentage of your overall grade. So if you're not too happy with either one of your test scores, do know that you can make up some points with your final as long as you just study now, get ahead on that and be super prepared. And you also have homework assignments and iClickers that should probably be 100 or at least close to 100%. And that'll only help your grade in the long run. Yeah.
Do they comment panel or is it up to their discretion?
I believe it's up to their discretion. So if you're in Dr. Altimos, it'll be very similar to what you're experiencing right now, where it has some multiple choice and some short answer. It'll just be a 2-hour exam length instead of a 50-minute. So it's consider it like double the questions. And then I think Dr. Bengali is also doing multiple choice. I think you have a different professor, but it should be similar to whatever exams you've been taking right now. Trying to think of anything else. I think that should be it. Any questions for me? Yeah.
So the final's higher than the lowest exam, they average the two and then that average replaces the lowest exam?
No.
Is that how that works?
Nope. It's just your direct points from both of them will contribute to your overall score.
Okay, because I thought the low.
That's not good.
No, math it gets fully replaced.
I just.
I don't think so. I think this one is whatever points you get out of 100 or out of 200 goes directly to your overall percentage or to your overall qualitative number of points. So if you had 180 out of 200 points and you have 180 out of 1,000 points for this class. And then that just contributes all to the 1,000.
There's no curve.
No. At least not that I'm aware of. So that's up to their discretion at the very end, but I have not seen one, I think. Any other questions?
The lowest midterm exam score will be replaced with the average of the final exam percent score and the lowest exam score.
As of the syllabus?
Yeah.
Interesting. Okay, well, maybe that's the case. I thought it was just your grades, but maybe she changed that this year or something. But she did give you a grade calculator, so you can use that as well. Anything else? Yep. Yeah, content's fine. Yep. It's time. It is. Yep. Let me just respond to that. Yes. So when we talk about specific heat, what does this relate to? Where do we see specific heat pop up? Whether that be a concept or an equation. Yep, great. So we have Q is equal to MC delta T. Here, or Q is equal to MCAT is the what you might know this as. And where is specific heat here? What variable does that pertain to? That's C. Yep, this is your specific heat. So when we talk about specific heat, this is telling you how much energy you need to put into this thing in order to heat it up 1 degree. Does anyone know the units for a specific heat? It could be kilojoules, it could just be joules with some sort of energy. Is that it? Mm-hmm. Is that it? Yep. Right, so the units for specific heat is an energy, whether that be kilojoules or joules, divided by grams times degrees Celsius. So they're saying that for this specific amount of weight of a material, in order to raise it by 1 degree, you need to put this much energy into it, okay? So does anyone know of something that changes temperature pretty quickly? There's faster ones than that. Aluminum, right? So any type of metal usually is pretty good at transferring heat. So metals usually have low specific heat. We call it SH. Okay, so these are sometimes in the question going to be 0.71, 0.9, even 1.1, something around that, right? Those are the values you're going to see for metals, maybe sometimes even lower. Ice is something that changes heat fairly quickly. Ice or solid form of water has a specific heat of 2.86, I believe. I might be slightly off, but it does start with a 2. Might be 2.1. It's 2.18. But then water, on the other hand, does anyone know the specific heat of water? Right? Water has a specific heat of 4. This is telling you that it's hard or easy to heat up water. It's pretty hard, right? You need a lot of energy in order to raise that water by 1 degree. So this, right, you see in everyday life, our oceans are not boiling, right, all the time because the sun cannot give us that much energy in order to evaporate the water. But when you need to boil a pot of water on your stove, right, you have to turn it up to high heat. Or if you put high heat on it, it boils faster than if you were to do it on low heat. So you need a lot of energy transfer in order to raise your material, water in that case, up to the correct temperature. Any questions on what it means? Does that help answer your question for specific heat? Okay, great. So that's specific heat. How we use it is in terms of this Q value. What does Q stand for? Q is your heat, right? This is energy being transferred. This is heat being transferred. If Q is positive, what is happening to it? It's absorbing, right? So if Q is positive, oops, that's a G. It's absorbing or taking in heat. What do we call that if it's absorbing heat? That's endothermic. So if Q is positive, is that the system or the surroundings? We'll call it. It's usually the system, right? Usually the system's what you're going to be basing off, is going to be basing off of. Sometimes it can be positive, sometimes it can be negative, but we'll call that the system here. So if the system is Q and that's positive, what's happening to the surroundings? It's losing heat, right? That heat has to come from somewhere. It has to be taken in from the surroundings. So if Q is positive, that means that the surroundings have negative Q, which means it's doing what to its heat? It's losing heat or releasing heat. And what do we call that? That's exothermic. Right, so in this process, there's an equal and opposite of transfer happening. Whatever Q is being gained or whatever heat is being gained by the system, the surroundings is losing that. It's the same value and has the same rate, right? you're changing at the same, or changing temperature, right, and transferring that heat. Not necessarily to the same degree, but at the same time. So what does that mean for our equation? If we have Q is equal to MC delta T for our system, what does that mean for our surroundings? It's negative and it's equal to that, right? The opposite. So Q is equal to negative Q. This is the system and this is the surroundings. This is really important when you start looking at calorimetry questions or just transfers of energy between the system and the surrounding, because if we can say that Q is equal to MC delta T, then we know that MC delta T is equal to negative MC delta T. And then this brings up a lot of questions where you can either find the mass of the system, right? Sometimes of what's being, that energy is being transferred to. You can see, try and solve for the specific heat. You can find that final temperature or that initial temperature. But right, that transfer of energy is happening, or the transfer of heat is happening between the system and the surroundings in equal and opposite fashions. What do we know about the end temperature for your system and surroundings? They're going to be the same, right? So your transfer of heat stops when T final is equal. Right? If you have something at 100 degrees and something at 0 degrees, they're not going to stop at 25 and 75, right? We're going to stop when they both reach that same final temperature. Does it necessarily have to be directly in the middle? Because that comes down to the mass of the objects that are transferring heat between each other, and it also comes down to the specific heat of those objects that are transferring, right? But it's going to end up somewhere in between the two initial temperatures of your objects. But they will come to a equal final temperature, because then once they're at the same temperature, there's no heat difference to transfer between the two. Okay, does that make sense for Q is equal to MC delta T? Any questions, or what questions do we have about this? Okay, do you want to practice one of these? So for this question, we have a chunk of copper weighing 16.7 grams and originally at 87.55 degrees Celsius is dropped into 85 grams of water at 25.33 degrees Celsius. We know the final temperature is 28.15. So I want to know what the specific heat of copper is, and we given the specific heat of water. Okay, so one thing I like to do whenever I have these kind of questions is kind of annotate the question. So if we have a chunk of copper weighing 16.7 grams, what is that going to be? That's going to be our mass, right? This is a mass. We have 87.55 degrees Celsius. What is that? That's T initial. Okay, and we have it's dropped into 85 grams of water. What is that? That's also a mass. And that's at 25.33 degrees Celsius. That's initial of water, yep. And we know that the final temperature is 28.15, so that's T final. And we're looking for the specific heat of copper. Okay, and then we're given the specific heat of water. So how does our equation usually start out? Yep, so Q is equal to MCAT. And what do we know about the system and surroundings here? This system is negative, right? So, or one of them is going to be negative at least. Okay, and then we know that Q is equal to negative Q. And which one's going to be negative here? Why copper? Yep, so your copper is going to go from 87 degrees Celsius to 28 degrees Celsius. So when you're looking at the temperature change, are we going high to low or low to high? We're going high to low. So that means that T final minus T initial is going to be what? Negative, right? And so that negative temperature change is telling you that it's losing heat. So that's going to be your negative Q here. At the end of the day, it doesn't matter which one is actually negative when you're solving just an equation. It's just if you're asked which one's losing heat, it's going to be the copper. The water is the surroundings. Yep. So the water would be the surroundings because the copper goes into the water and is going to transfer its heat out to the water. All right, so our copper is losing heat. The negative sign, as long as you remember it, will cancel out no matter what. It's just easier to cancel out a negative with a negative. So we're going to have your positive Q is going to be your water, and your negative Q is going to be your copper. So when you set this up, you have your mass of water, which we said was 85 grams. We have our specific heat is 4.18. And what is our delta T here for water? And how'd you get that? Right, this is T final minus T initial. Right, oh, it's always going to be final minus initial. That's going to equal the negative of the mass of copper. X is our specific heat. We don't know that. That's what we're looking for. And what's going to be our delta T for copper? Great. Right. So when that negative value of 28.15 minus 87, or yeah, 87.55 is negative, that will cancel out our negative at the front of our negative Q. What are our units that are left once we do the left-hand side of the equation? Just joules, yep. Right, your grams are gonna cancel out from the 85 multiplied by 4.18, and your delta C cancels out from your T, delta T. And then and what units are left with the right-hand side of the equation? Yep, it's grams times degrees Celsius times X. And how do we solve for X? Yep, we can just divide. So X here. Right, we see our units come back into play. So we have joules, grams, degrees Celsius, and that's gonna match our specific heat units. And we end up with 1.01 joules per gram times degrees Celsius.
How come it's T final minus T initial for delta T?
It is, whenever you're changing anything, it'll always be final minus initial. So that's just like the rule of the change. So it'll always be final minus initial.
And then when you're trying to decide if it's absorbing heat or like heat,
Mhm.
it's check like if it's going from a high to a low. So initial to final.
Yep, so you're gonna look at initial to final and you're saying, okay, that's going from high to low. So I'm losing temperature and that's gonna be heat here. So in order to lose that heat, you have to give it off. So if you were to do the math for final minus initial, you have low minus high, which will give you a negative value. And then that would be, right, indicated an exothermic reaction or losing heat.
Then whichever one has that negative, you're gonna put the negative on that.
Yep,
Okay,
yep.
just cancel out.
Absolutely, yep. If you did not do that mental check beforehand, this is just a way to like make sure that you know which one is supposed to be positive and which one's supposed to be negative. Or if there's an additional question that says like, which one is losing heat here? You should be able to have a way to check which one's losing heat. But if you were to put the negative not on, right, if this was a positive in the initial, right, we made positive 16.7 and we put the negative over here. The negative value from your temperature on this side here would make this whole side, the right-hand side, negative. This is a positive from all of your multiplication here, and then you have your negative here. So they eventually will cancel out. It doesn't matter if you get it perfect for which one's negative, which one's positive. It's just a mental note to say, okay, I know this one's losing heat. This one should be my negative Q value. And then it makes everything positive, and that's easy to work with. Yeah.
What's the, we kept having to like, kept saying like, oh, things that are in a most stable state, you just knew like what it was. How do we know what's like the most stable?
Great. Any other questions on this before we move on? Does this make sense how you use those equations between the system and surroundings? Yes. Yep.
And you use the Q for calorimetry, right?
Yes. Yep. And Q can mean different things for different types of calorimetry. So you just need to familiarize yourself with that. Sometimes you have a calorimeter, and that will give you a calorimeter, specific heat. That will have the mass already taken into it. So it'll just be joules over degrees Celsius, right? You might see what do they call it? Right, you might see calorimeter constant pop up in a question, and this could be something just any value, like 35.5. And it'll just be joules per degree Celsius, right? That's like taking the MC delta T, that's like taking this MC portion and doing the multiplication separate, right? You have the mass and that specific heat multiplied together to give you 35.5. So you don't see that mass unit in the constant anymore because it's already been taken into consideration. Okay, and then you can just use that directly as C delta T, we'll call it, right? And that's just for the calorimeter. Does that make sense? It's like you wouldn't even be given the mass for the calorimeter because the constant that they gave you was like separately they found the mass and separately they did that. They did the specific heat for that calorimeter and they just gave it to you directly, right? You don't have to do that. They already did it for you. The calorimeter would come into play for your Q for the surroundings, right? So if we had a calorimeter constant for this most recent equation, it would go with your heat for the water. So instead of it being just this Q on this side for your water, you would have, right, Q of water plus the Q of the calorimeter. So you would have two separate values here. And those can just get added up together. The calorimeter would have the same delta T as whatever that surroundings is. So in this case, it would be the same delta T as the water. Did I lose people or did we follow? Good. Alright, so when we look at the periodic table, this is not given to you on your periodic table that you have on your exams. But if you familiarize yourself now with what these are, then it'll just, you'll be able to use it later and you'll remember it. But when we look at like P table online, they do categorize it. Does everyone see the solid, liquid, gas in like the upper left corner? Right next to beryllium and magnesium. Yes. So that categorizes this by, they use colors to categorize by solid, liquid, and gas. So if we look at lithium, beryllium, right, groups 1 and 2, we see that all of those are in white, as in comparison to the hydrogen right above it, that's in red. That's showing you that all the metals there are solid, right? And their most elemental state, what they are on the periodic table, they are a solid. It's showing you that hydrogen is a gas, right? So that's what they mean by elemental state. What does it look like without touching it? Its most stable form is what it is on the periodic table, and that's going to be either solid, liquid, or gas. For any of your metals, what do we notice about almost all of them? They're solids, right? And that kind of makes sense, right? We think of aluminum, we think of copper, that we usually think of a solid like sheet of metal when we think of those. So all of your metals, whether that be lithium, sodium, those are all going to be metals in their most elemental, or solids in their most elemental state. So you're looking for an S, and that's going to be 0 for heats of formation. Right, and that's just saying you don't need to form this, you don't need to do anything to it because that's how it comes, right? For your non-metals, right, your nitrogen, oxygen, fluorine, we have to remember that those are gaseous and also diatomic. So this is where those diatomic elements come into play again. Do we know which ones are diatomic? Hydrogen is diatomic. Where else? Yep, fluorine, oxygen, what else? Chlorine, what else? Bromine, what else? Iodine. I think there was one more.
Nitrogen.
And then the nitrogen. Yep. So how I always remember this is that if you look at nitrogen, oxygen, fluorine, that's 3 across. Fluorine, chlorine, bromine, and iodine, that goes 4 down. right? That makes a little 7, but that's only 6 elements. And then you just need to remember that hydrogen is your 7th, right? So on the periodic table, you can visually see a 7. They're just in that corner, and then you have to just remember hydrogen. So if you need a heat of formation of any of those, if it's diatomic, it's a 0, right? It comes as a diatomic molecule. You don't need to make it diatomic. If you just want one oxygen atom, then that's where you need some energy into it, right? You need to split that bond and then to create 2 separate oxygen atoms. So that's what it means by elemental state. Does that make sense? Kind of memorize it, but you notice that almost all of your diatomics are gas. And if they come as a gas, it'll usually be in their elemental state. Or if they come as a diatomic, then it'll usually be in their elemental state. Yep. Bromine's a liquid, right? So it would be Br2 liquid would be a 0. Yep. Right. If you remember your periodic trends, as we go down the periodic table, are we getting heavier or lighter? We're getting heavier. So what does that do to your IMS? It increases. So as IMS increase, what happens to your state? Right? It doesn't boil as well. And why is it not boiling as well? There's stronger IMF, it's more stable, and the stronger IMS we have, the more solid like it gets, right? So as we keep on increasing down the periodic table, fluorine and chlorine are still going to be gas, but as we go to bromine, it gets a little bit heavier, a little bit more harder to boil because it's more liquid-like, right? It is a liquid. As we go down to iodine, we have even more atoms or even more electrons in our system, and so now it's going to act even more solid-like, and so it's going to be even harder to boil, right? So it all goes back into that. Any other questions? Yep.
Can the stable form be a 9?
In a stable form can be an ion, but it's not going to be its elemental state. When we talk about energies of formation or enthalpies of formation, it'll be as its solid non-ion form. And that's because an ion is created when energy's put in or removed from it to remove an electron, or put an electron on. Okay. Great questions. Anything else? Speaking of enthalpies of formation, is energy required or released in order to break a bond? Required, right? All bond breakage requires energy, so that will always be a positive value. Does bond formation require or need or release energy?
Release.
That releases, right? All bond formation will release energy. So bond breakage requires energy. Bond formation releases. Positive delta H, and this is a negative delta H. Enthalpy, yep, and delta H is enthalpy. What other letter did we start talking about? Delta H is related to Q. Q is heat transfer, H is more energy transfer. Any other questions? Yep.
With it, like, it makes sense, it needs energy, like, to, or is it just like automatic thing that just forms, so it like.
Yep, so I don't know if they showed this graph, but when they look at, this is like energy. When 2 atoms are 2 completely apart, they have infinite amounts of energy. So they're way out here. And when you bring 2 atoms close, it creates this trough. And then this is like ideal bond length. So this would be like a fluorine-fluorine bond is that much, right? It's most stable in that trough. But if we get a fluorine-fluorine, right, where they're super, super close together, we create a lot of high energy between them because the positive nuclei are too close to each other. That starts creating repulsive forces, and the atoms don't like that. So that ideal bond length is where it sits happy. And think about if you're carrying something and then someone puts a hand right on whatever you're carrying to help you lift the load. That's energy release because you don't need to put as much effort into it. So that's kind of what's happening with the bond here, right? It's holding on to that energy and then it's starting to share it. So it goes to a lower energy. Whereas, right, if you think about trying to break a board or something, right, you need to put energy into that two sides in order to break the board. And so that's the same thing for a bond, right? You have to break that thing in between them. Okay, any other questions? Yep. In terms of like the delta H of a reaction or yeah, okay. So like when I see like how that comes into play. Okay. So we'll do this one here. Right, so if we just have a generic equation, A plus B goes to C plus D. We're saying that for this reaction of, right, a double displacement, we have a delta H of negative 300. We'll call it kilojoules. If we have a delta H, this is the enthalpy of reaction. So is this an endo or exothermic reaction? This is an exothermic reaction. If it's an exothermic reaction, is energy being absorbed or released? It's being released. So does that mean it's acting as a reactant or as a product? It's acting as a product, right? So I want you to think of enthalpies in terms of stoichiometry as, is this a reactant or a product? So instead of it being a separate entity, I want you to think about it as A plus B goes to C plus D plus 300 kilojoules, right? So saying that for this stoichiometric ratio, I get 300 kilojoules. So if I had right, 2A reacts with excess B, how much energy is released? 600. And how did you do that? Right, you multiplied it by 2. You just use your stoichiometric ratios. You're saying that I have 2A, and for every 1A in my reaction, I get 300 kilojoules. So if I have 2A, then I could just multiply across, and now that's 600 kilojoules. Yep, so if it was then instead of it being a product, it's now a reactant because we need 300 kilojoules of energy in order for this reaction to happen. So then it's actually and the same question can still be asked, right? If 2A reacts with excess B, this time it would say how much energy is required, right, for this reaction to go to completion. In this case, it's still 600 kilojoules because you still need that much energy to go all the way across to your C plus D. Does that make sense of how that works? It's generically. Okay. I use the word excess. So what does that mean? Types of questions can be asked here. Percent yield, what else can it be? Limiting reagent, right? So think back to exam one, right? What does it mean to take a limiting reagent? What does that mean? And think about ways that you can solve limiting reagent questions. If you're asked a limiting reagent question when it comes to enthalpies of reactions, you don't have to solve for how much energy can be released, right? You can solve for the limiting reagent between actual products to see which one is the limiting reagent. You can solve for energy, but right, if that confuses you, just solve for a product. And you can go from there. Okay, but just nothing ever leaves, I promise. I actually just read a paper last week and it brought back an equation you'll learn in probably next week or 2 weeks. So I've looked at that equation for 8 years now and I'm still talking about it. So if you continue with chemistry, it never goes away. And I promise that. So, any other questions on this? Okay. So for do a reaction, you can say that all right. So for this question, we have the formation of ammonia requires 298 kilojoules to go to completion. And if 9.18 grams of nitrogen reacts with excess hydrogen, how much energy is required? I want to change this. We'll make that easier. All right, we'll say nitrogen gas. Okay. So what do we need to do first? We need to balance our equation. How are we going to do that? Three hydrogens. Two ammonias. Looking good. Okay. What else do we need to, and so what's next? Yep, so we need to determine if it's endo or exothermic. Which one is it? Why do you say endo? Right, requires is saying you need this at the start in order for this to happen. So requires as that like key word is going to be an endothermic reaction. So we can add our 298 kilojoules to the left-hand side. Okay, what's next? Good, so we need to convert our grams to moles, right? We still don't like working with grams. You can't directly relate these things. So we do need to get to moles. So we need to say that 9.18 grams of N2 1 mole of N2. Does anyone know the molar mass of hydrogen or nitrogen? 14.01. So 2 of them would be 28.02 grams of N2, right? We have 2 nitrogen molecules. We need 2 values. That is 0.328 moles of N2. And where do we go for moles? You can use your stoichiometric ratio so that we're saying that for every 1 mole of N2, what do we get? 298 kilojoules. That's about 97.6 kilojoules. Okay, questions on how we did that?
So the 97.6 kilojoules is saying for every mole.
Yep, so that they're saying in order for all of that 9.18 gram of nitrogen to be converted into ammonia, you need 97.6 kilojoules of energy. Any other questions?
The amount of grams of ammonia. And then. So you have to use.
Yep, right, you can always go backwards, right? If they're saying that this amount of grams of ammonia was produced, how much energy was required, you could just go backwards that way. They could ask you, okay, so we're saying that we have how many grams of ammonia is produced when 500 kilojoules of energy is applied to the system. So how does this change our stoichiometric ratios now? What are we starting with? We're starting with our energy, right? We're starting with our kilojoules. So instead of the 9.18 nitrogen that we grams of nitrogen that we started with, now we're saying I have 500 kilojoules of energy. What ratio do we use now?
1/298.
1,
2.
2, right? We still have to use that coefficient of ammonia in front. So for every 2 moles of NH3, we need 298 kilojoules of energy.
Yeah.
It's still created a reactant, right? Because we're saying that this amount of using the same chemical equation as above, right? So we're still saying that this requires energy in order to do. Yep. Yep, still apply. Yep, still being a requirement for this reaction.
Wait, so the 97.6 is the energy required for the reaction?
The 97.6 is the energy required to convert 918 grams of nitrogen to ammonia.
What about like 298?
So that's just saying that if you had 1 mole of nitrogen, which would be 28.02 grams, you would need all 298 kilojoules. But we don't have a whole mole, so we're going to use less energy, right? Yep. So that's always a good check too, right? At the very end, you see, okay, I have 97.6, but it required 298. Does that make sense? And that's why I stopped in the middle at the moles of nitrogen, because then you can see you have less than a mole there. So you should have less than a mole of energy for your overall answer. Okay. Mhm.
Like with the 500, you don't add that into the equation, or like, would you like add 500 on the left side of the swing?
Nope. So we're saying that it's still saying that 298 kilojoules is required for this reaction to happen. But we have 500 to give, right? We have more than enough needed. So we're saying, okay, if we use all of this energy, how much can we get? Right now we're saying our nitrogen and our hydrogen are our excess reagents, and the 500 is like our limiting reagent, right? We're going to use all of that up. And how much do we get from there? Okay. Can we stop at moles of ammonia? Nope. What do we have to do there? Yep, we have to convert it to grams. So 1 mole of NH3 is 17.04. So before I even do the math, right? We have 500. Is that more or less than what's required to do 1 mole? It's more, right? So we should expect more than 1 mole of your NH3, right? Or I guess more than 2 moles of our NH3 at the very end. I end up with 57.18 grams of NH3. Okay, any other questions on that one? Does that make sense? Just kind of ringing a bell of what we did first exam? Yes. Does that help answer your questions? Okay, anything else? How do we feel about thermo? Do we get it? Is it hard? Iffy? Yeah, I feel like this is always like the iffy one.
Just getting it's negative or positive.
Yeah, for the most part, as long as you know where energy is being transferred to or from, you should be able to at least follow the energy. Right, you have to know that for work being done on the system or work being done by the system, right? Heat's transferred to the system or heat's transferred out of the system, right? That's where all of that wording comes into play, right? These are very much word questions, and you have to pick out the words that are responsible for giving the clues to your questions. Okay, and the most advice I can give for thermo is just practice, practice, practice. So if you look up chemteam.info, you get this cryptic website, but I promise it is amazing. If you click on that hyperlink, it brings you to all of your different, I guess like topics that you might see within like Gen Chem. And you can see in this bottom of the second column, there's thermochemistry there. If you click on that one, then it brings you to a whole bunch of different hyperlinks with a whole bunch of different questions that you can look at. So you have tutorials and problem sets, right? So it's just time, temperature. You can look at one of these and it'll bring you through it. There is a bunch of Hess's law right here, right? 11, 12, 13. So you can do some Hess law questions if you're struggling with that. Specific heat questions here for 2. You can kind of give you a little synopsis at first, and then they can just go through there. And then, right, same thing with molar heat of vaporization. So if you're looking at the melting curves of things, it'll bring you through some examples. It'll give you an example, and then the solution will kind of explain the solution. So highly recommend using this website to your advantage, not even just for thermochem, but like studying for the final 2. It just gives you more and more practice to look at. And then the more you practice, the more of the wording you're going to get. And that helps you out a lot. It is chemteam.info.
And then is our fifth quiz, for all of us, is it just thermo stuff?
I think it's just thermo stuff. Should be like where you stopped after the exam or right before the exam.
Final, the previous.
Yes, so your final is cumulative. There is more emphasis on what you haven't been tested on yet, but there are still some questions from the beginning of the semester that you've already been tested on. Yes, I will work on that like Thursday, Friday, and over the weekend. I will make sure I have that up by Sunday at the latest. Anything else?
Things like, I don't know, is that just like all chapter 9?
Yeah, pretty much all chapter 9. Highly recommend just like reading through those notes again and then like circling or writing down on a piece of paper like all the formulas you see, just so you can kind of be like, okay, what is that formula? When do I use it? Where do I recognize it? So I don't think a lot of this is given to you on your formula sheet. I think Q is equal to MC delta T is, but not like some of the relationships. So just reference what you find in the notes and compare to your formula sheet as well. Alrighty, we'll call it good there then. Keep out for the lookout for practice problems, and then if you have any questions in the meantime, just feel free to send me an email. Thank you. I'll end it first real quick.